Hi boys and girls. In the last video we have discussed the BPSK model, mathematical model of BPSK and the signal constellation for BPSK, the effect of AWG and all that. You saw a demo Python code depicting the effect of AWG on BPSK symbols. Now today we will see, based on that mathematical model, we will see how the transmitter and receiver are made, and we will understand how what is the variation of the bit error rate with the signal to noise ratio. So let me start with that presentation. Now the objectives of this presentation is that you will learn about the BPSK transmitter and receiver. Then you will demonstrate BPSK transmitter and receiver with Python code and plot the BER-SNR curve. And you will compare the BER-SNR curve for both the actual transmission as well as the theoretical case. Then I will tell you how this transmitter and receiver are implemented using physical hardware, that is with a USRP, set of USRP. USRP is a universal software radio peripheral along with the lab view. So in the last video we discussed the mathematical model of BPSK that says that the BPSK signal is nothing but the bit sequence BIT into root of 2 EB by T cos 2 pi FCT. Okay, so first there's a binary stream here coming here. There's a binary stream of ones and zeros. Then that is converted to a Bohr non-return zero encoder. This is nothing very fanciful or nothing it's just like the streams of zeros and 1 are converted into streams of -1 and 1 just by maybe if this is B, a to B minus 1 will make it a bipolar sequence. It will be a sequence of -1 and 1 that is multiplied by phi t, the basis function, that is nothing but root of 2 by t cos 2 pi FCT. So this is the transmitted signal SIT. It will be S1T and S1T and S2T corresponding to -1, bit -1 and bit +1, or logic 0 and logic 1. Now this transmitted signal that goes through an additive white Gaussian noise channel and it is received here. Okay. Here what we do is this is a coherent receiver. That means the received signal that is multiplied by the basis function. This basis function is available in the receiver as well because it is a mutually agreed thing that this is my basis function. So that is multiplied by root of 2 by t cos 2 pi FCT, and this is integrated over 1 bit period. Hope you remember what a bit period is. I told you in the last presentations I showed you a waveform with some 100 nanosecond bit duration. So for that 0 to t, integrate it, and then you get some fixed value. So as I told you earlier, my threshold is at 0. Based on this threshold I make a decision. If this value is greater than 0, then I say that 1 is transmitted. The 1 is missing here, but Ri is 1. If it is greater than 0, Ri is 1. If it is less than 0, then the received bit is a 0. So this is how I make a BPSK receiver. Now let us see how this is implemented with Python code. So I'll go to that. Now as usual I import SciPy and PyLab, and I assume that number of bits is 100. So the transmitted bit is I use the sin rand -0.5. 1 plus that makes it a bipolar type signal. No, it's a 0-1 signal. Then I make it a bipolar by this trans bits is a random sequence of zeros and ones, and x this is a 2 times transmitted bit -1. It makes it a bipolar non-return zero signal. So then I have to define a carrier. So for that I put say t equal to 1, some unit time. In that I define a time vector r from 0 to t with an increment of 0.001. And I take the carrier frequency to be 5 if c is 5, and I define a carrier as root of 2 by t cos 2 pi f ct. And this is the total number of values in the carrier, length of the carrier vector. Now I initialize BPSK array to null, a null array called BPSK array. So then I initiate a for loop in the range 0 to n. If this xi value is 1, that is if it is a logic 1, I append a carrier to the BPSK array. Carrier is nothing but root of 2 by t cos 2 pi f ct. Or else if it is a 0, then, or if it is a minus 1, BPSK is array is appended with the negative of the carrier, that is with the phase reversal. Then this may be multiple array, so I concatenate into a single array. So the BPSK signal is a concatenated version of the BPSK array. Now I have to transmit this signal through an AWGN channel. So ultimately I will have to plot the bit error rate against signal to noise ratio in dB. So I define a noise level in dB from say minus 60 to 10 dB with increment of 2 dB. So the actual value of the noise variance will be 10 raised to minus 0.1 into this. Just a conversion from dB to the value. So then I compute the energy of the bit using this equation, that is half of variance of carrier. This half comes because it's a sinusoid. Then I compute the signal noise ratio CB by noise variance. Now I convert that into dB. SNR dB becomes 10 log SNR. Now I have to receive the signal. Now this noise is generated. Noise should be added with the signal, and I have to receive the signal. For I have to know how many bits are in error. Suppose I transmit 1000 bits. How many bits are in error? If I transmit 1000 bits and if 10 bits are in error, then the bit error ratio is bit error rate is 10 by 1000. So for that I initialize, for storing the BER values, I initialize a BER array, that's a blank array. Then for j in noise variance, I generate a noise signal that is square root of rand length BPSK signal. So it is equal to the an equal length noise is generated. Now the received signal is mixed with noise. The BPSK signal is added with noise. So this is equivalent to unadditive. This line is equivalent to unadditive white Gaussian noise channel. Now during every bit interval, I have to integrate and dump and see whether the value is positive or negative. So for that I initialize a blank receiver array, and during one bit interval I try to compute the coherent, the integral, the what you call the integrate and dump thing. So what I do is, instead of an integration, I perform a summation here, because these are all discrete values. So this is my locally generated carrier into received signal for every bit duration. So this whatever is coming under this thing is the received signal during one bit duration. So if this intermediate value, then that is stored in an intermediate variable inter. If the inter is positive, you append 1 to a receiver array. If the value is negative, append 0 to a receiver array. Now the received bits are there. Now I have to compare the transmitted bits with the received bits. Some may be in error depending on the level of the noise present. So what I do is I compute the total number of bit errors. So I take the difference between that, take the absolute value, and sum it and divide by the total number of bits. I get the bit error rate. This bit error rate value, BER value, is appended to the BER array, and then I plot it in a figure. First I plot the BPSK signal just to understand the signal. Then I come here, I plot the bit error rate array against SNR dB in some green color, and I label it as the experimental value, because actually bits are transmitted and received. Now at the same time, I have to compute the theoretical BER. This we studied in the previous video. That is a half error function complement root EB by N naught. So that is computed this way. The theoretical BER value should be zero point 0.5 into, this is part of the signal processing routine. The special functions, that is a error function complement SQRT EB divided by noise variance. This star star minus 1 is a division or inverse. So then I put some title. So then I plot the theoretical BER on the same GUI. Okay. Now let us run this code and see how this happens. I open a terminal in this thing. I type IPython. Type run BPSK trans.py. Now first I see the BPSK signal. If you zoom the signal, you can observe the BPSK signal in this. I zoom it again. We can see the changes in phase during the pattern. Every time when the phase changes, there is a every time the bit changes, there is a 180-degree reversal of the phase. Now we are more interested in the bit error rate. We can see this curve. This dotted curve shows the theoretical BER. This is this curve. This dotted curve shows the theoretical BER. This is nothing but the plot of half error function complement root EB by N naught. And this wiggly curve, that is the theoretical BER, the one we computed by transmitting the bits and computing the error. That this is the variation in SNR is from some minus 40 dB to some 30 dB. Okay. I can see that at 0 dB, that is at 0 noise, we can see that the signal, the bit error rate is much below 0.1, meaning that the system is working well. So at 0 level, if this is equal to or greater than 0.5, then the communication system is useless, because if with no noise, if half of the bits are in error, half of the bits received are in error, then the communication system is completely useless. But here this is not so. But here if you see for SNR equal to 0, signal noise ratio 0 dB, if you come here, that is well below the 0.1. Okay, so less than 10% of the bits are in error at SNR at 0 dB SNR. So here the error is more. The bit error rates are more because there is a great amount of noise in this. This is a very poor SNR. Minus 30 dB is a very poor signal to noise ratio. Noise is more and signal is less. So when it comes here as this improves from 20-30 dB, you can see that the all bits are received correctly. So that is how you understand the bit error rate versus SNR curve. This is the most important curve in any digital communication system. Let me go back to the presentation. Now this is a curve we explained. This is a result of the execution of the Python code. And this is another experimental setup. This is a real-time communication system. This I did when I was working at College of Engineering, Karnataka. And this device is called Universal Software Radio Peripheral. This is a similar unit. Okay, and this is an NI product. Okay, product of National Instruments, a bit costly product, and this is based on LabVIEW. So what we do is there is a built-in FPGA in this, and the code is created like this block diagrams. In LabVIEW, everything is created as a block diagram. Or graphical, it is basically graphical programming. So what we do is we generate a block diagram like this and download this block diagram into the FPGAs in this USRP. So each USRP has its own antenna. So this may be working as a transmitter, and this is working as a receiver. So we can how in real time how the communication happens. And this transmitter VI is a something called a virtual instrument. Is a block diagram in lab view. So this is a front panel of the transmitter. You can see that here I can set up this transmission frequency, the IP address, etc. IP address of the system that we are using, the frequency user. And here you can see in this chart, you can see the signal constellation. Of course, it is shifted by 180 degree, 90 degree. So this is one point, and this another point. Two points are there in the signal constellation. So if you look at the receiver, I have a block diagram here for the receiver. Once this block diagram is drawn, that should be downloaded to the receiver USRP. It resides in the FPGA of the received USRP. And you can see that this is a receiver front end or receiver. Here also you can set the transmitter frequency, the IP address, and all that. You can see that there's a slight tilting from the vertical line. There's a slight tilting. This is due to the phase changes and all due to transmission through the atmosphere, even though they are kept very adjacent. So you can see the effect of noise and all that here. There is a slight blurring, there is a slight elongation of the signal constellation. So this is how it is done. So when you come to the end of this presentation, what you have learned is you understood the block diagram of the BPSK transmitter and receiver, and you observed the demo in Python, and you understood how it is made in a USRP. But this USRP is very, very costly, but you can have low-cost USRPs like ETS, etc. So with that, you can write code in Python and download into that. So you can you understand the real-time communication. This has a lot of applications in wireless communication. So many job opportunities are there. So then you observe the plots of variation of theoretical and practical bit error rates with SNR. So with this we come to the end of this video. I thank you all.